everything practically. So these two, extremely important. And therefore, you always need to remember that in these solutions, I will have to use the solutions because designs are open-ended problems. There is not one single solution to the problem. You can make it in many different ways. It's just the performance of what you're going to create is not going to be the same. One of these possible solutions is going to have the best performance. All right. So you try to incorporate that into your design early on. So you understand that if I use transmission lines, I will have to find the smallest possible size. Now, it is also possible that in your design, take this one. This is your antenna. All right. And somewhere in here, there is a source and a power amplifier and whatever else is used to be able to have that communicate with a Wi-Fi or with another receiver. Okay. Now, if inside here, your source that generates the power is somewhere there, that means that you have until you have to go from wherever here physically speaking. I don't know exactly where it is, somewhere here. The rest is batteries, and they're always on the lower end. So there's going to be somewhere here. They try to bring it as close to this one, but not, you cannot bring it right there. So you need to have this much space, for example, to connect your source to the antenna. And this space, physically speaking, does not mean anything until you know what kind of frequency you're sending from this. If I judge from the size of this antenna, which is called the monopole, probably it's very low frequency. All right, because usually that is going to be close to a quarter of a wavelength. We did not cover that, but if this is a quarter of a wavelength, so this one and an image somehow that it creates because of the ground creates half a wavelength. And then this is a quarter. How much is that? You say 4 inches, kind of. So half a wavelength is 8 inches. All right, to figure out how low frequency this is. So 1 wavelength is 16 inches. Multiply that by 2.54, whatever it is, inch per centimeters. Then you're going to see how many centimeters this is. I believe it might be even, well, it might be like a 200 megahertz kind of frequency. So this size does not mean anything until you know how much is your wavelength, all right? Okay, so you will have to use something to go from here there. And therefore you will have to do the best you can so the maximum power from here goes here. Because if I can send here the maximum power, then I can have a longer distance to communicate. All right, that's simple thinking. Now, what does that mean? The shortest possible line to do what you need to do. And what else? It means, now in the second, if at the end of my solution, whatever I do, I find an input impedance here, I need to have an input impedance there, which is going to give me the maximum possible power from the source to this transmission line. So the input impedance there to get the maximum power from the source, how much should it be? Remember the matching or the conjugate matching when it is. Now everything is real here on the front end. So how much, if R sub S is 50, what value of the input at AA prime is gonna make the real power from the source to be maximized as it goes to the antenna? Yes, 50. All right, 50. So you know that no matter what you do from matching, okay, this has to be 50. That's how you start thinking, 50. That's what I'm saying. Every choice has to be justified, all right? Otherwise, if you make a choice and you think that nothing justifies it, or there was not a driver to have you find this solution, there is something wrong in your solution. Okay, so now I go here and I write it. I wrote it here as clearly as I could because I would like you as for Friday, I'm not going to give you anything else. I would like you to read this carefully before we start Friday, all right, for the lecture. So because this is a best, I say that is 50. To match the antenna to the source, we need to make Z input at AA prime to be 50 ohms. Okay. Now, if I want to, let's go back to this one. If I want to make Z input at AA prime 50 ohms, it implies that I have to find a transmission line where this is real, obviously it's not, with a length, given length, which is going to transform a complex load to a real. Okay. From the things that we've learned, some simple matching components. Do you remember when we discussed the quarter wavelength transformer? Okay. The quarter wavelength transformer, to repeat it, it can do, even if it's easy because you know it's a quarter wavelength, and then you know that characteristic impedance is going to be the square root of the load to whatever it has to match it, 50 ohms. The only problem is that it only works when the load is real. All right. So since here this is not real, that means that the way it is here, I cannot use a quarter wavelength transformer. So the answer to the first question is no. And I did that because I have to tell you, in a class like this, because the quarter wavelength transformer is something that we learn very early, and then everything else comes later and is a little more complex, people will immediately go to that, but you cannot use it. Then eventually they get like characteristic impedances which are complex numbers. You should never, ever, if you ever in your solution find a characteristic impedance of a line which is a complex number, that you definitely have made a mistake. There are no lines with complex characteristic impedances, all right? They are not made. We don't have them, we don't want them, because a complex characteristic impedance means a very lossy line. So nobody's gonna use it. We can make one, but it's gonna be so lossy that nothing is gonna go to the antenna. Okay, next question. Can you match this antenna using a transmission line and a lumped element? Okay, so here the question is giving us something more. It's giving us, they say, okay, since you cannot match it with only a transmission line between the source and the antenna, then I will allow you to add something. Let's try to see, can we add a lumped element? Not that you can always do it, because the smaller it gets, the more difficult it is to put elements like this, all right, to solder them. You may do it in hybrid, very low frequency, maybe that may help, you know, because it's very large, you can see, but you cannot do it on a phone. You cannot put like elements like that on a phone. Okay, but you can put it in something bigger, maybe, because it's easier and less expensive. All right, so in here we allow us to do that. Okay, let's think about it. Since I know, you know, if you don't know many things, you have to rely on the few things you know, right? So we know the quarter wavelength transformer. Okay, since I know that, I would say, what if I were to add something next to the antenna or close to it, so I could then cancel the reactive part, all right? So the reactive part is positive. To cancel that, what do I need to add? A capacitor, because the capacitor gives me a negative reactance. All right, so if I were to add a capacitor in series like this, then the sum of the two would give me something like that. So practically I add the capacitor and I change the reactance of the load, but I change it in a way that I force it to become zero. And when does that become zero? When C is equal to that. And it happens only at one frequency. So I optimize my solution at what we call the design frequency. And what is my design frequency? 10 gigahertz. So here I will put, so 10 gigahertz now in this problem is my design frequency at design frequency. And design frequency, a lot of times even you can put it like this, is 10 gigahertz. But you don't have it. I will remove it here so you don't get confused. All right. So at the design frequency, right, the capacitor, all right, who has this value. So that at the design frequency, this one goes to 0. And what happens if I just go a little bit away? Well, it's not going to be exactly 0, but it's going to be very small. All right. So if I place everything in there, it gives me a value which is reasonable of a capacitance of 0.5 picofarads, which is very reasonable for that frequency. Okay. So if I were to use that capacitance and put it there, that means then I reduce my circuit to this one. Since the capacitance neutralizes the inductance, the capacitor neutralizes the inductor, in other words, then what is left is the real part of my load, which now I have to match to R sub S. Okay, now I can use the quarter wavelength transformer. Okay, what that means is that I choose this length, it says quarter wavelength transformer. It means that the length is a quarter of a wavelength. So the length is going to be 1.5 centimeters. A quarter of a wavelength, no, 3 centimeters, 0.7, 5 something centimeters, right? 7.5 millimeters. Yeah. And then Z sub naught is going to be the square root of this value times this, which is 50 times 100, give you 70.7 ohms. So if I follow this approach, yeah, I can find a solution, and that's the solution. What it gave me, I specified both L and Z naught. And I have a solution, yes.
And this is only valid really at that 10 gigahertz
Yes.
frequency. Right?
Now, there is no design that applies to more than one point. Every design has a design frequency. What people will try to do then, with something that we're not going to talk about this because it becomes more complex, is there are some other requirements. Not only you want it to work at one frequency, but you want it to be broadband. What it means is that as you move away from this frequency, I don't want all of these values to go off very fast. So there will be other, so in higher level classes, when you do design of circuits, you will learn how to do broadband designs. But at this moment, when we try to design something, is one frequency. And then you know that if you don't do anything, it's not gonna have a catastrophic failure the moment you move on 10. It's gonna fail, but it's gonna fail graciously. Not really very, you know, it's gonna be, sometimes it's gonna be the bandwidth may be, I mean, you measure it. Sometimes can be 5%, 10%, broadband can be 50%, but you know, how graceful is the failure. If it's very, very graceful, then it's gonna be more broadband. If it's, you know, but it's not catastrophic. All right, the moment you go off by a little bit, it's not like that everything goes off. Okay, and that's because of the elements we are using, because all of them are linear elements. Linearity, all right, extremely important. Also, we don't talk about this at this moment. Okay, now somebody can say, well, fine, now we did that, that's good for this kind of application, but I want now the same for my phone. And my phone, I want to be so small that I don't want to have lumped elements to put in there. I want to be at a higher frequency, 10 gigahertz, and I want to have everything integrated. So obviously, we're not going to do that. But they give you a suggestion. So the suggestion is, what if can you max, the suggestion comes as a question rather, can you max this antenna using a transmission line and a stub? And we said the stub is nothing else but another section of a line that is like shorted or open at the end. Now, there are, as we will see by solving this problem, the two different ways of using a stub. But let's start thinking, first of all, maybe I need to do that here for a second. And I don't know, I have a little bit of a problem adding new pages. Let me see. Okay, let me see whether that is gonna happen here. Let me see whether I can add page. All right, worked. So let me show you two ways that I can put a stub on a transmission line. Okay, if I have a transmission line, let me use this one. And this is one line. Let's tell you, it's not working today. This one, right? And then here. And let's assume that I have a load somewhere here. An impact. Make it, okay, like this to understand which one is. Okay, and this is the load for an antenna for us. And this is my source on the other side. I'll show you two possible ways you can put a stub. One is in series. It means I can select anywhere on the line from the end of the line. Okay, this is the input port, A prime, output port, B prime. From anywhere between AA prime and BB prime, I can select to place a stub. One possibility is what we call a series stub. And let me, so for a series stub, what I do is that I cut the line somewhere on one side, small, and then here I connect another line, even if it shows big, in reality it's a small size. And here I put another line. Yeah. Yeah. This is another line. It has different characteristic impedance, obviously. So this one has a characteristic impedance Z0. This one has a different characteristic impedance, Z0. It could have a different, or it could be the same, but I will call it Z01. And this here is either open or short at the end. All right, so it's either open, as I have it here, open circuit, or it could be shorted like this, and then you call it a short circuit. All right, but I'll leave it for now open. Okay, so that if I place a stub like this, then you will have to put here a new set of ports. All right, so let's assume that you call them C and C prime. And then you will also here have to put a port, even if the line is not divided up here, you will need to put a port. And then let's assume you call it D. All right, you always need to remember that the distance between the ports, it looks big here, but it's very, very tiny. Okay, that's a series stub. A parallel stub, which is another possibility, is exactly what I have here. And then I copy and place. All right, but as the word says it, so I will remove that from there, remove this here. Okay, so in this particular case, I will still, I will continue my line here, in fact, with a bigger size here. And then I will create another port somewhere in the line here, which I will call this D. Let me call it as before. Ah, it's very thick. So this is D, D, and D prime. And then here I'm gonna place the stub like this in a parallel way. So the stub is gonna look like that. Yeah. Like this. And it can be open or short. In this particular case, I can do it short, so you see that this possibility. All right, so that's short. And that still has a different characteristic impedance. So this is, in fact, how I can use the stubs, all right, either in series or short, but what is gonna be of the two depends on how you do your design, and whether it's gonna be open or short depends on which of the two is gonna give you the shortest length in the stub. So we'll do that now, since we said that. So you see what the stubs are, we are gonna start solving this problem. Okay. Now, what is it? Now I have introduced some other unknowns that I have not defined. Not only I have not defined this one or the length of this line, I have now introduced this stub and I have not defined the characteristic impedance of the stub and the length. I have not defined those. So I still do not know, therefore, this here. And I still do, and now I have introduced and then I will call it this a best to remember it's for the stub. And also I don't know this characteristic impedance. Okay. Four unknowns, therefore. In a case like this, when you have these kinds of problems only with transmission lines or sections of transmission lines, my suggestion and what we always follow is that we set the two characteristic impedances to be the same for simplicity. We don't change the characteristic impedance between the stub and your line for a number of reasons, but one is simplicity, all right, in the solution. And therefore, I can say 50 ohms, which is the standard, all right? So when you do distributed, with the exception of the quarter wavelength transformer, where you define it from the square root, in any other application of a design problem, where you use transmission lines, if you only use transmission lines, or if you use transmission lines and a lumped element, choose your Z naught to be 50 ohms. All right. So here in the solution, I choose, first of all, I start with the transmission line. I choose Z naught to be 50 ohms. Okay, because I have not introduced a stub yet. I'm still dealing with the line. Eventually we'll do them. This is too extensive, but for you to see the process, all right? We're not gonna do that kind of extensive layout in the future. So now I know whenever they ask you to use multiple transmission lines, then you know you have to use the Smith chart. Because if, with the exception of what we did with the quarter wavelength transformer and the lambda element, if you go to use transmission line equations in a problem like this, where you have to put a stub like that, it will be so complex that you will not be able to solve it. Plus, many of your unknowns, which are the lengths, will be inside hyperbolic tangents. All right, so it's gonna be very difficult unless you use the computer. And the Smith chart is gonna give you a much easier design, but also it's gonna give you a conceptual understanding. All right, a designer is not a person who runs the computer to design a circuit. The designer knows when it has to develop the architecture. He knows who are the biggest people in terms of hierarchy in a engineering company, the architects of the systems. These are people who are extremely knowledgeable in terms of what is possible. And before you even define, they will tell you, we are going to solve this problem. We are going to do it in this way. Now, it's not like that they sleep at night and they see some kind of a dream or something and comes out. There are ways, of course, you have to, but they have the knowledge. Usually, these are the people who are in charge of the large systems. They do the architecture. What we are developing here in a simplistic way is called the architecture. All right, they define the architecture. And then after you decide how you're going to solve it, then you have to go and define the specifics. If you have to define the specifics, if you don't know how to solve it and you go from equations to design a problem, it's not going to happen. I'm just telling you, there are no tools today to design for you, all right? In any case. So we define that. Then what we do next, we know we have to go to the Smith chart. So you have to normalize everything to all of the impedances that you know. You have to normalize them with respect to 50 ohms. So this, first of all, the antenna, because that's where we are going to start with. The antenna becomes normalized 2 plus j 0.6. Okay. Now, we do therefore take the load and we normalize it. And what is the first step we are going to do with the Smith chart? We are going to find where our load is. The load is what is connected to BB prime, right? Is this number. This line just shows that this is ZA. And we found that to be 2 plus j 0.6. Okay, how am I going to find it? The real part. Remember, we said all of the circles that go like that have their center along the horizontal axis, and they are like tangential to this point. All of these have one thing in common. All of their points have the same resistive part. They're impedances. All of the points, everything here shows impedances. All right, this is a map for impedances. And all of the points here have the same resistive part. And how much is that? 2.0. So I found the circle, all right, who has all of the points of my normalized load. So I know that my impedance at the antenna is somewhere on this circle, because all of them have a 2 here. All of these points here have a 2. Now, I need to accommodate that 0.6. I said that I put 0.2. All right, so then what we said last time, to be able to find the lines that where all the points have the same reactive component are these parts of the circle. All right, these circles are big and go like that, but these are the ones. So you go out here and you read these numbers and you go to 0.6